Okay, so all these young people.
Okay, welcome, welcome everybody. So, as you can tell, this room is too tight for our class. In fact, if every single person showed up, I don't think we would have enough room. But there are seats available, so please go ahead and find a seat if you want, or you can, hi Neil, how are you doing? Or you can do what you like, all right? But please make room for as many people as we can. And if you would rather have a little breathing space, today at least, please feel free to just watch the video later or stream or whatever you want to do, okay? Because it's running right now, okay? So I am thrilled to get to see many of you again and have a different experience than we've had in mechanics and materials, okay? This class is going to be different, and for those of you who remember mechanics and materials, some of you may have good memories, some of you may have, well, not so great memories, all right? We'll try to replace all those memories with wonderful ones together. Okay? This is Multiphysics simulations. A lot of this course was developed by Professor John Singer, Raman Payman, others as well have been involved. So we've been working on it. There's some similarities, some differences between what Professor Singer and I like to emphasize. Nonetheless, I think you'd find that we have a pretty good overlap in terms of the content and the material that's covered. What we'll try to do today is give a little bit of an overview. There are a lot of logistics to this course. There are a lot of intricacies. We can thank Professor Singer for figuring them out. And then we should be able to get to a little bit of a discussion about science, experiment and theory, the scientific method essentially, how it relates to this class. And then I'll hopefully not bore you, but I'll share a little bit about the research that I've been doing and how we've used simulations to get a better understanding of the physics involved. If you look at these slides, you'll also see that there's this 1.4. We won't cover this today, but there is a nice video that was done, I'm not quite sure, a little bit a while ago by Marco. And you can go ahead and review some of those fundamental skills in that lab if you like. So, information about the course. What are some of our goals? Well, we're going to establish a framework for modeling systems in the fluid, thermal, mechanical, particle. What other domains? Those are them pretty much. Okay, and you'll get a chance to look at some of the problems you've seen in your other classes and the analytical results, and say, oh wow, now I can create a pretty picture, or I can attempt to make a concrete simulation to describe that behavior. And if you took mechanics and materials with me, you'd hear me say, okay, baby steps, when it comes to simulation. We actually did some finite element analysis, if you recall. We were looking at what types of structures? We were looking at bars, shafts, beams. Those were pretty much the three that we used for the finite element simulations that we performed. So we're going to go beyond that by quite a bit and think about, okay, how do you make sure that your answers make sense? How do they converge on an actual solution? Okay. But nonetheless, we use baby steps. We want to compare as much as possible to the analytical results and then be able to go a little bit further. We will also try to explain what some of the limitations are and some of the factors that you're going to consider. Okay? We will look at one physics and one method at a time. It turns out that F equals K delta that we were talking about in mechanics of materials, that's Hooke's law, right? Where you have force, you have a spring constant, and you have some displacement. From a simulation perspective, mechanics are actually very, very hard. So we'll spend time looking at other partial differential equations before we get to mechanics, which will be kind of closer to the end, in fact. So some of the diffusion-based equations, those are much simpler to model. And then the finite element analysis that's employed with the mechanical problems. We will emphasize results. Okay, so what does this mean? From a practical perspective, the decision has been made, and I agree with it, that we're not going to look at your code. We're going to be looking at the results of your code, which means you're going to be generating figures. And we'll talk a little bit about what some of the implications ethically are about that too, as we proceed. Okay? But we're going to be focusing on making sure that the actual, the graphs, the outputs that you see, those are the ones that make sense. Okay? We will also emphasize research and communication. So as you'll see, if you haven't already seen, there's a great deal placed on a project report, the steps along that way to that project, and also a presentation, which will be in video format this semester. So these pictures actually are not exact simulations that you would do in this class, but they are representations of things that you would have either a complete ability to do, or you at least have some partial understanding of how to get there. So this one on the right will focus on orbital mechanics pretty quickly in the class using MATLAB. Mechanics, this is essentially looking at the stress in a structure that's got a C type of shape, and so we'd be able to do that pretty easily. This is going to be a little bit more complicated as when we talk to, when we get to kind of fluid structure interactions are one thing, and then heat structure interactions, that's kind of another. We'll talk about the finite difference method and how we can use that. We'll actually code. So before we get to ANSYS, we're going to do some coding and be able to run some simulations in MATLAB. And then this is kind of a simulation that looks at kind of molecular dynamics, and that's something that we'll kind of do at least between two particles at the beginning of class in MATLAB. Okay. So we're an ABET accredited department in two programs, aerospace and mechanical engineering. And so just to give you a little bit of background, we just went through, some of you were involved in helping us get reaccredited. Thank you if you were involved. Okay. And for those of you who are not so familiar, we go about justifying what we're teaching and how we're teaching it, and making sure that we are essentially providing an education for the complete engineer. So there are 7 criteria that we get to meet, and this course will work on the first one, which involves identifying and formulating and solving complex engineering problems. We'll work on number 3, hopefully how to communicate effectively, at least through your reports and through your presentations. You'll get to do a little bit of work on a team of 3 students, and we'll be doing lots of analysis, lots of interpretation of data, and hopefully we'll be acquiring some new knowledge and being able to figure out how to use that in other aspects of our lives. Okay, so is most everybody here now on the Canvas site? It went live, I put it up a few hours ago. Okay, good, so you have that. There should be a couple syllabi there. Okay, we'll get into the logistics of that in a minute. And we'll be using the DSV lab and the EIT labs. All right, so do most of you know where these labs are? Okay, all right, good. The contacts. So I'm Aaron Mazzeo, and then would our esteemed TAs like to introduce themselves? Min, you want to introduce yourself a little bit first?
Yes, I'm PhD student. Professor Shen. I'm in TA for this class.
Right, and then Kai?
I'm Kai, and I'm also a PhD student, and I'm working with Professor Velasquez, and I will be one of the TA in this course.
Right. Okay, so if we pull up the syllabus, you'll be able to see. Okay, here we go. All right. So the three of us are available over, I guess you could say, digital communication. If you'd like to get in touch with Min, he can get to you through Canvas, but his preferred method is through email. And Kai and I our preferred method is through Canvas inbox. Okay. For those of you who know me, sometimes my inbox doesn't get the attention it's due. So at least if it's in Canvas inbox, when I go into Canvas, I've got everything there. All right. So trust me, it's a little. You'll make sure that I get to it with a reasonable amount of time if you use Canvas inbox. We have office hours Mondays, Tuesdays, Thursdays, and Fridays. So no Wednesdays, and they're there. Okay, you have the Canvas site. If you haven't already, go ahead and add yourselves to the group meet. So with the group meet, and I can, if I like, I can switch. Should I switch over? So with the group me, and there's a QR code if you want one. Okay. The idea here is that you can work together to solve, discuss problems, and the TAs and I, we will work on responding, to kind of group questions. If it's an individual matter, though, I'm sorry, but try not to do the @me. All right, try to just send me a message in the Canvas through Canvas if you could. All right, so that I will make sure I try to address it that way. Okay. There are different topics in the group me. So there's one that talks about what happens here. There's one that talks about what happens in the labs. There's one that talks about the final project, and then there's another topic that talks about the guest lectures. Now these are virtual guest lectures, and we'll get over how some of these things work as we continue here. We will have, there's one Zoom link. Okay, there's one Zoom link to rule them all. All right, and that link will be what the three of us use for our office hours, in addition to being in physical locations. Okay, so the DSV lab is free, so Kai and Min, you can use that because that has all the computers, of course, in addition to using the Zoom. And with this course, a lot of times you're going to want to share your screen. Okay, I don't, you don't need to share your video, but you're going to want to share your screen to show us what's going on, so that we can kind of provide some feedback. So Zoom is a good way to do that. So even if you're in the same room with us, all right, you might want to have Zoom installed on your computer so that you can share it, or you can just show it to us too. Point at the screen if it's that small crowd. All right, but Zoom is going to be our friend there. Okay. Now, these are what we call the non-lab sessions. What we're doing right now in fiber optics, and that's pretty much it's like a lecture. Hopefully, we'll have some communication, and then the lab assignments will be in DSV so how do you say it? Okay, so here we go. This is actually, so this is over here. The labs will be and DSV and EIT and DSV and actual.Zoom, all right? It turns out, and this is a little bit embarrassing, we have so many students in this class that we need to have a virtual section for the labs, okay? So we will not physically fit in both of these labs if we split the class even in 2 halves. Oh, actually we would, but it's not, okay, sorry, better said. EIT is not available during our Thursday afternoons, okay, for another class, sorry. So what we're doing is putting everybody in these different locations. Okay, so now, okay, I was looking at one thing and showing another, of course. Let me flip back. What in the... Does anyone, oh, you gotta be, here we go, all right. Mac is, I'm not really great with a Mac. All right, sorry. So EIT, DSV virtual, and DSV and EIT. So we're going to have a group project right now. Okay. So I hope everyone has access to this link right now. Okay. What I need is your participation. Right now, everybody is in either Group A or Group B. And if you're the student who just got on the canvas, I haven't even added your name to this list, okay? What you'll see is that we have everybody's last name and first name. In fact, since this is, I should probably do it over this other spot. Hold on a second. Let's go back over here. What I need, okay. What I need everybody to do is evaluate your group letter, A or B. All right, I'm going to explain what that means, a little bit more detail. And your lab location. So you'll see some of you are in DSV, some of you are in EIT, and some of you are in virtual world. Okay? No. Where's the... Hold on. Let's pull this up. Okay. So some of you, right, and you see that we're in red. We're in the red in 3 of these categories. Okay? So if I did this right, what you should be able to do is change your group and change your lab and get us to have all greens across the board. Does that make sense? So we need to reduce the number, of people in group A by 4. Okay? We need to reduce the number, or group A and DSVB 125 by 4. We need to reduce the number of group A and EIT by 4. And we need to reduce the number in group 3 and DSV by 3. Yes. This is in the syllabus. Yeah. Okay? So, okay, so hold on. Before you go, right? Hold on. Just listen for a second. This is an opportunity to hang out with your friends if you like. Okay? So you can pick the same group and same room as your friends if you want. Group A, all right, a little bit more information. Group A will have its labs on Tuesdays. Okay? So there is Group A and then 2 subsets. You're either EIT or DSV on Tuesdays. Group B is on Thursdays, And there are two subsets, EIT and virtual. Okay? So what we need to have happen here is we need people to essentially move into the virtual section. Okay? That's what we need. Now, you ask, what are the benefits of being in the virtual section? Well, you don't have to go to the lab. All right? And you'll have the Zoom going, and you'll be able to ask questions of your other virtual teammates and of the PAs. Yes, Kevin?
Can you talk more about the timing for both the lab and the lecture?
Okay, so today is the only day all semester we will be in the same room. Okay, I know it's sad. All right, it's very sad. Thursday, this coming on Thursday. Actually, group. Did I get it flipped? Did I say group? Yeah. So, yeah, Group A will meet in person in FBO 108. That's what I said. Okay. On Thursday, Group B, you get to do whatever you want. Ideally, you're thinking about your final project. Okay, but you're not in any location. Group A will meet here on Thursday. Tuesday, Group A will be in lab. EIT and DSV. Okay. Whoops. Okay. So. Yeah. Okay. So. Okay, thank you. All right, is this clear now? That's mud? Okay. All right. Yes. They're good, right? They're good. Stop the counting. Yeah. All right. Okay. So. Okay, so make sure that you're on this list. After, like, tonight, or probably, to be honest, tomorrow morning, early tomorrow morning, I'm going to go and I'm going to lock everything down, okay? And that is what we're going to have. Okay? But thank you. So that was interesting. That's very interesting. Okay. Just in terms of where people running. Don't worry, the TAs are going to alternate. So you're going to get experience with each TA. Alright? We've agreed that you're going to flip. Okay? Any questions on this? I've never done this before. I thought, why not? Give it a shot. If you cannot behave, or if we cannot behave, if everyone cannot agree to a nice and minimal solution here, then the executive person will take charge and does make decisions. All right? But here you get freedom. Okay? All right. Thank you. Yes. It's not letting you edit. Then ask a friend to help you edit. Because I don't know why you can't edit.
It's just high traffic.
It's high traffic? Okay. Okay. All right. Are we not Okay, so yes, this now what will happen, okay, is you in Canvas, you will have the ability to see either the group A or the group B syllabus. Okay? And we'll get that all straightened out in terms of what's going on. The short end though again is that if you're in group B, okay, which is this syllabus actually over here, okay, your job for Thursday is to just think. Alright? Right? And if you want, you can think in DSV because we have it reserved. Alright? So there you go. At the end of the semester, Group B will be going right up until the deadline. Alright? With a lab, the last day. Group A, at the end of the semester, will have an off week. Okay? To think about their project. Alright? So that's the trade-off. Group A, okay, so here's how the labs work. Okay? So the labs do have a time component to this, alright? We will release the labs way in advance, hopefully. Alright, so for everybody. Alright, right now, I don't think they're up. Okay, because I was like, there's so much information here, I just unpublished a lot of stuff. I gotta get some of the details worked out. But the way it will work is there will be a video that describes exactly or nearly exactly what you have to do for the lab. Right? So you're going to be either typing the code almost identically to what you see. All right? And some people argue, well, this is no thought. It's just copying. Okay, that's maybe true, but nonetheless, people do make their decisions not to do the labs. All right? Those labs will be due 20 minutes after that lab session. Okay, but you can do it before, right? But you're guaranteed to have a TA there for the last hour and 40 minutes, essentially, before it's due. Okay, so you can get that done. Then there's a post-lab session of questions. Significantly more difficult. Okay, in many cases, but right, you've done the lab session, which will help you do the pre-lab, right? So this is like the opposite of what you often have in classes, right? Often in class you have the pre-lab and then you go in and do the lab. Here, in the lab, it's kind of like the pre-thing, because then you had to go and do some more simulations on your own, and they're significantly more difficult. Any questions on that? Okay, so yes, the group A will have their due dates before group B. Alright? But on the flip side, group A will have a little bit more time, maybe at the end, to work on their final project, or they just will be a little less stressed. Should you collaborate? Absolutely. Okay, on these. That's expected. Well, it's not, okay. It's expected that many of you will collaborate. It's not expected that all of you will collaborate. Okay? Any questions on how the labs are going to work? Okay. There will be due dates, of course, for the post labs. I was tempted to say, oh, forget the due dates, just get it done. I think having the structure is helpful in this case. All right, so you know what's going on, you get it done. Especially the labs, not the post labs, the labs, because they are really doable. Okay, they're very doable, and then you can get it done and you can focus on your other work. Now, the grading. How does that work? Okay. 45% is based on the labs and post labs. The final project paper is 23%. There are going to be project checkpoints along the way. We'll give you some feedback so that the final paper is not a huge surprise, hopefully. And then you have a video. Given the size, we've never had a class this big. Okay, I'm nervous about this. Already you can see that I've made some little mistakes here and there. Okay. So in the past, when I taught the class, or one time I taught the class, we took 2 sessions to have everybody give a 4-minute talk. There's no way we can do that in 2 sessions. Okay? So what we got to do instead is we get to do, you're just going to upload your videos. All right, and if you want to share those videos with the rest of the class, I'm happy to do that. So we can have like public, like if you put it on some whatever social or not social, whatever platform that has a link, right? Then like I can share them with the class and everybody can enjoy them. But we're not going to be able to enjoy them in the class together. The groups. Okay, well we'll talk about the projects in a little bit more. Attendance is survey. So yes, your attendance is worth 5% in doing the surveys. How do we do the attendance? Anyone have any guesses? Yeah, we do the selfies, all right? So, just to practice, okay? You don't like it? All right, so to practice, there's a 0-point exercise that you can do right now, okay? So, just so everyone, if you have issues with your camera, whatever it is, but for those who have not done this before, what you do, okay, is you let me get out of the way. You don't want me in there, okay? And you take a picture of just your face. It's surprisingly easy to just respect the privacy of other people and get your face and the screen, and then you upload it in Canvas, all right? So if you see right now, there should be an available assignment, okay? Okay. All right, we got preset. Oh, let's see some cameras going.
Well, every lecture.
All right, so the labs, you don't have to do this in the labs, okay? The labs, you have to get the labs in by the appointed time, all right? Whether you show up to the lab or not, it's okay, all right? That's not a big deal, all right? But for these sessions, we do want you to take this out. Okay? I would like you to do this, and you get credit for it. And I think you'll find that when we get to a smaller class, conversation's a little bit easier. I've noticed this. Yes?
Miss a lab, can you go to a different session?
Okay, so the issue is that the deadline still holds. All right, so if you, so I mean, if you wanted, if you're in group B and you want to like jump in and do it early with group A, and there's space, we're not going to be opposed to that, but we want you to kind of respect. Like, obviously, the whole class cannot do that, right? It'll just swamp us. Right? So we do have the structure in place for a reason. But yeah, if you're in group A and you wait, it's going to be, it'll be commonplace.
So if you miss a lab, how can you make up?
Okay, so if you miss a lab, you can always, so we have in place a policy. Okay, good. All right, so here's the policy, right? Late assignments, all right, you can always get, the maximum penalty on a late assignment is 75%. That's a lot, okay? But that's the maximum, right? So every day it's late, it's 25% off. So that's the policy. And of course, if you have an absence that is what we can consider to be an emergency or some activity that is, excusable, just communicate with us, with me, all right? And we'll get it taken care of, And there are two requests for that. So if you know you're going to have, if you've had an emergency accident or absence, like an emergency absence, let the dean of students know. That goes into the registrar, and it shows us, yes, you've been absent, and it sends me a message if everything's working like it's supposed to be working. And then, of course, you should contact, as it says there, you're supposed to also contact the instructor. Okay, so that's what we expect. You all are juniors, though. By now, right, this is like, you've got this, right? Okay, so let's talk about the reports a little bit. Oops. Okay. So the reports, the group projects, you get 3 members in a group. Yes, let's see, I don't know if the whole number of students we have, or the natural number of students that we have, or natural, whatever it is, either one, right? I don't know if that's going to be divisible by 3, but we're going to hold to this as much as possible. Okay, so it's 3 people in a group. Right? In another iteration of this class, every person does their own project. All right. So, but here we're going to do 3 in a group. It's going to be a little bit different, though. Okay, in that we will do peer-to-peer evaluation. All right. So hopefully, what I hope is that everyone agrees that everyone worked, nicely on the project, and everyone gets the same grade. Otherwise, right, we'll just scale people's grades. So some person could get, unfortunately, theoretically over 100%, right? If their 2 group mates ditched them completely and they did a fantastic job. That is not what we want. Okay, any questions on that? All right. Some of you may be in senior design, capstone, right? So maybe there's something that in that project you would like to simulate, right? Maybe there's something you're interested in. A lot of people like to simulate airfoils, nozzles, things of that nature on the aerospace side. Okay, we'll go through a little bit more on the projects. I guess maybe we could. Well, we're talking about the grading. We'll get to that in a minute. We'll also talk about writing. And then the final project video is going to be 4 minutes, and it'll be like a 2-minute video, almost like an advert. Okay, I don't know what you guys call it. Promo. What do I say? TikTok? I don't know. Okay. 2-minute promotional video. All right. And then 2 minutes of you kind of giving a lecture. All right, justifying what you did. And so that's pretty much. I mean, that's how the projects and the final projects kind of considered. As you can tell, it's we got about 45% on the simulation-based exercises and 45% on your final project. And then the extra 10% is based on your attendance and insights on the guest faculty lectures. So there will be like 7 or so guest faculty lectures. You get to pick 4, and then you just write like a quick little blurb in a discussion on Canvas of what you learned, and then you get credit for having watched that. Okay, does that make sense? Great. Okay, and then the class participation is just for the bump. All right, and we already talked about that. Okay, so each project will need some type or some kind of hypothesis. All right. What is a hypothesis? All right, so we've all been doing science for a while. What is a hypothesis? Yes, you want to say something, Federico? Yeah.
It's like an educated claim to how an experiment or how a phenomenon will occur. And
Yeah. Okay. So it's some type of educated claim. Usually, right? Like we'll talk about observation comes first, right? Before you've observed something in nature, something falling, whatever it might be. Okay. And then you come up with a hypothesis, and the word that I think can almost ensure that you have a hypothesis The word is depends. Okay? If you squeeze the word depends in, you can be pretty sure that you're making a hypothesis. So you could say the coefficient of lift is going to depend on the length of the cord, or something like that. All right? The coefficient of lift is going to depend on the angle of attack. Right? The amount of stress the structure can bear will depend on the effective cross-sectional area of that structure. Okay? If it's in compression or tension, right? The word depends. So this is kind of, you're going to try to test your hypothesis. Now, you don't want it to be a throwaway hypothesis, right? You want it to have some degree of intricacy in there. And you want to think about how you will test the hypothesis. Do you prove a hypothesis with one experiment? No, right? You can disprove a hypothesis with one experiment, but you need a number of experiments to kind of prove or put something into what we would consider to be a theory, to go beyond hypothesis. Okay? We want there to be discussion. If you look when it's up and you look at the rubric, it's not up right now, I don't think. What you'll see is that we do weigh the discussion portion of the paper, of your work, heavily. Okay, so that means that you need to create some data for there to be a discussion. And maybe you also need to look at the literature a little bit for there to be a discussion. So you're going to not try to, you're not going to simulate a 747 or an A320, in flight, right? That's, for multiple reasons, even from just the idea of calculating lift and drag, doing that 3D turbulent, it's just impossible for us, okay? But, maybe you could do something like, oh, here's an airfoil, and if I change the curvature a little bit here, that changes the effective angle of attack, and I see that camber allows me to have a higher coefficient of lift, which would be similar to what I see when I lower the flaps on my airplane. I don't have an airplane, but if during landing and takeoff, right, that's what happens. The flaps go down, and that allows you to have more lift at a lower speed. Okay? And allows you to, get into the air or get out of the air. There could be projects where you're thinking, one person is going to do this component, one person is going to do this component, one person is going to do this component. It's not an absolute requirement, okay, but it is a possibility, and then try to put them together. Very hard to do successfully, to be honest. Okay? Don't necessarily suggest that approach. I'm fine with, okay, we worked together on a simulation, so-and-so was doing more of the gathering the information, so-and-so was doing a little bit more on the comparison to the actual experiments, and we get something all together, right? A nice project is to have a hypothesis, again, and also maybe to even start with some baby steps, saying, hey, my simulation does, like the NACA 2012, whatever it is, but like when I put in this airfoil, it matches up with this experiment from the 70s. Okay, and now, since I've got all my parameters set, I'm going to do something a little more complicated. And so we're looking at discovery, so doing some observations, making a hypothesis, getting some results, doing some analysis, and then having some discussion about what you've done. Okay. All right, any questions on the project? I have one or two more things I want to say about the project. To do that, we'll go down to here. All right. So, can you use Google? Okay, go ahead. What's up?
Is that a final project, or is that like a course?
So, your project can change. You're going to have different checkpoints where you're going to say, hey, this is like a proposed project. Okay, and I'll be like, okay, okay, yeah, things about and then you go on, you're like, actually we don't like that anymore, so then we're gonna do this. And then you get to this next step where you're like, this is our first simulation, like a converging simulation, or actually a initial simulation, right? Then a converging simulation, then like a kind of, these are my simulated data, and then into my data, right? So you can change as you go, right? But we're gonna have checkpoints along the way so that it's not like just one big thing that you, or you can make it that way. If you say, oh, I'm gonna change my mind, I'm gonna change my mind too, and then yeah, you're gonna have a lot to do with it. But you're not, the beginning is not exactly what you're doing. So I think it's wonderful that we have some great tools now for that exceed. I mean, you know, when I was a student, Google had just come out. Well, maybe not just come out. Yeah, it wasn't around that long actually. And so that's how we got information. Okay. Yes, you can use all these different tools. That's great. Please use Grammarly to correct your English, for goodness sake. When I was in middle school, I think I learned that there was a general rule that you were supposed to cite something if it wasn't general knowledge. Okay? So the expectation here is that if it's something that's kind of a little bit obscure, or if it's a number fact or a physical fact, I mean, if you put out, you know, the suggested market for widgets is $100 million, okay? You better have a citation for that. That's kind of, right? You have to have a citation, right? Or it'd be really nice if you said, look, so-and-so has done this study, so-and-so has done this study, so-and-so has done this study. This is how my work fits in that, right? You need to have citations. You need to have citations. And if I click on one of your citations and it's a fake citation, that's going to be a problem. Okay? So, the expectation is you've got all these tools, but you better have citations that are relevant to what you're talking about. And anyone that's used any of these tools knows that they can create interesting citations. Okay? Or maybe not anyone. Have you done it before? Maybe, okay. Try it out. Say, what has Sam Smith published in 2024? Whatever, put their name in. And you'll get some that are actual. Okay, and maybe I'm dating myself now, but this is like, when I was doing this a little while ago, you get stuff that's not, this is not real. And that's fine. That's not to say the tool is bad. It's just to say that you got to make sure that you know what you're citing. Okay? So, and then you also have to be able to describe what you're writing. Okay, so those are the expectations. We create a lot of figures in this class. A lot of figures, a lot of images. Just you gotta, your simulations have to be real. Okay? And I can't guarantee that I'll catch it, but I'm pretty sure I'll catch it if it's garbage simulation. I mean, if it's garbage simulation because you ran the simulation and it's garbage, right, because it doesn't match reality, that's one thing, okay? But please, please, please don't ask for an ANSYS-like simulation that describes this and, you know, just puts it out there, okay? Let's talk. I mean, in order to do that kind of thing, arguably it's going to be more work to make it look like bad stuff, or make like reasonable stuff, and not using the software we're using than just to use the software that we're using. Okay. Any questions on this for the reports? Yes.
You asked like AI to write basically like not the foundation of the code, just like a head start of like what we should be looking towards, and then we adjust it a bunch.
Yeah, I mean, I would appreciate a citation on that, right? Okay. Now, I will say that the software that we're using, and you'll see the videos that we produce, the first parts in MATLAB, we give you the code. Like, it's there. You're like, usually the post-lab exercises are like a few lines. So, I don't know, maybe, you know, maybe these algorithms have learned, maybe Gemini has learned well enough how to like get the result that you're looking for, at least on the lab exercises. But for the we don't emphasize, I just added today a little section on scripting and automation. That'll be the last thing we talk about. A lot of what you're going to see is actually based in the GUI. So you're going to be doing a lot of pointing to it. Right? So, so I don't know. I don't know if we can generate a workbench file or the code. I'm sure you can. I'm sure if you ask it to do APDL or something, then maybe you can do that. But yeah, just for your own sake, do try to like use. And if you don't, and if you have good stuff that comes out of the AI, cite it. There are ways to cite it. If you look at the AI higher education website for Rutgers, it has ways to cite. I don't want you to have to cite every little Google search though, right? Like if you're like looking for information, you don't have to cite that you use AI necessarily in my class at least to like say, hey, that's how it went. But if it comes up with a citation or with some not general information, then you better go to the original source or close to the original source and put that in. Zotero is what I recommend that you use if you haven't used it before. Maybe you've heard of EndNote, some of these others. Rutgers has a license for EndNote, has a license for RefWorks. Pick one and use it. It makes your life really easy. Pretty easy with references. Okay. Any other questions on that? Yes?
Is there a certain format you want to see?
So it'll become more clear. There'll be different sections that we want. Okay? Well, there'll be different sections. But it'll become more clear as we go. Okay? All right. We are going through time. I looked at, and also just, we are in the red just by 2 people for Group A and DSV. But we have 3, so we have 3 slots in EIT. So if 2 people can move from DSV in Group A to EIT, if you're willing to do that and you do it with a friend instead of me having to pick a couple people, I really appreciate it. Okay, so we're really close. We're really close. Okay, so some common questions. How much coding do I need to know to do well in this class? So how do you say it? I think when I saw, so you can watch Professor Singer in some of his old videos, and he'll say no. You don't need to know anything. I kind of agree. Nonetheless, we do have this Fundamentals in MATLAB lecture that was created by Marco a while ago. I think it would be good if your MATLAB's a little weak, then spend some time on it for the next few weeks. And we can talk about it in office hours. It's pretty critical that you understand the basis of MATLAB. We will transition off of MATLAB, but the data you generate in ANSYS, I often put back in MATLAB just for the sake of plotting. Okay? So you want to at least be able to plot things pretty quickly and comfortably in MATLAB. I think that's the way to do it. Okay? Yes, you can use Excel, but it's just taking 2 columns of data and putting them in a matrix. Like, I'm not even saying you need to create a data file. Just copy and paste them into the stick-in script, and then hit plot x comma y. It's pretty simple. Okay, but if you haven't done it in a while or ever, I understand it's scary, right? We will probably eventually move to Python. So for those of you who, not this semester, okay, but for those of you who are like, oh, MATLAB, hello Python. All right, will the tutorial sections be recorded? Okay, so the tutorial sections or labs, yes, they will be. Okay, and really the goal for the TAs is to guide you through them. All right, so you'll be watching a video, and then you'll be putting in your, you'll be just, like some people, they take their phone and they watch the video, and then they put it on the screen, and then they're working on a computer terminal. What are the hardware requirements for this class? Okay, so If you're in the virtual section, take a look at what the hardware requirements are on the website. Essentially, it needs to be, so the website being ANSYS's website, I think now they've upped it to you need 50 gigabytes of hard drive space. There used to be 25 gigabytes of hard drive space and 4 gigabytes of RAM. Okay? It's not through the roof. All right? It's really not, but if you don't have a PC, okay, so that could be problematic, right? So you got to also have a Windows machine for ANSYS. MATLAB, use whatever version you want. Okay? Are the groups different, meaning group A and group B? No. So, okay, we're gonna cover the same material. It's just one we cover. Okay? And can you change topics? Yes, you can change topics for the final project. All right. So here is Professor Singer's guide to potential project topics. Okay? So he has here some happy and not so happy faces. All right, so you can see here, if your project is a 1D simulation of a particle, that's probably too simple. Okay, but if it's, let's see, fluid structure interaction in 3D, don't do it. All right, don't do it. That's what Professor Singer will say. Okay? So this is also from Professor Singer, this is kind of the sweet spot where you want to be, potentially. Okay? Again, you don't have to have the most complex project in the world. That's not what we want. It's not what you want. Okay? Trust us. You don't want that. But even then, even if it's not the most complex project in the world, I mean, it is perfectly normal for a simulation to run for multiple hours. Okay? It's not good if the simulation runs for multiple days. That's a problem. Okay? Because you need to be able to test the hypothesis. So in order to test the hypothesis, you have to vary the parameters. And if you can only run one experiment every 3 days, you're not going to have many parameters to test. Okay? So keep this in mind. And this graph, of course, will mean more to you as we get through the semester. Okay, so here are some topics. Okay, so trajectory of a falling glider or ball. All right, so one place you can look for projects also, I think, feel free to use the ANSYS knowledge base. Feel free to use COMSOL. Okay, I think the COMSOL tutorials are really, really good. Okay, so Professor Singer was like, there was an uptick in projects about balls and pitches and golf swings. And guess what? There were some really good COMSOL tutorials on these very topics. Right? So yeah, feel free to use the resources. Please cite them. All right? What I'll try to do when you put your initial projects in is I will go through the internets, and I usually give people like 4 or 5 links of like, hey, this is what's out there already. Okay? So, and it also helps me calibrate and understand what's out there already. All right? And so you want to make your lives easier, just use the material, but cite it. Okay? That's perfectly fine. Heat sink, all right? Those thermal problems, they can go pretty quickly, all right? If it's just conduction or even some levels of convection, if it's natural convection, and you have a boundary condition that's appropriate. CFD laminar, okay, so fluid mixer, internal pipe flows, laminar flow, okay, low Reynolds number. You can do stress on, say, a falling drone leg, okay, that's one. And then in 2D, you could do some CFD, turbulent flow, and then you can also look at some fluid structure interactions in axisymmetric phase, and actually some axisymmetric mode. Okay, so, I hope that as we go on, some of the things that you will learn in the class, okay, involve physics. there's a big push right now for us to teach AI, and I think the department will get there. All right. There's also a bunch of people who are like, do our students know the basic physics yet? Okay. This class will hopefully, the way we're teaching it right now, ingrain the physics. AI will be is wonderful, and it's a great tool for trying to bridge certain parts in the physics that are very complicated. ANSYS has released an AI simulation module. I've been told, at least, and you can fact check me, internet if you like, but I've been told right now that's not available in the academic license that we can have. But we've got plenty to cover just in basic physics, stuff that's been around for, hundreds of years, or decades even. All right, some of this stuff is more recent. How do you effectively master this material? Well, I think you get what you put into it, you get out of it what you put in, and coming to same old things. If you're struggling with things, talk to the TAs, talk to me, go to the computer labs. We can help you out here. This class, it's not so much about having to memorize things and perform, right? Mechanics and materials, better or worse, that's how the class runs, right? You have to have a good understanding, and then you have to be able to put that out in a pressure environment. Here, we can work with you on things, all right? If you give us enough time, if you give yourself enough time, we can work through things together, okay? And we talked about some ideas for a final group project. All right, administratively, that's about all I want to cover. That was a lot. The class has a lot of moving parts, so it's kind of complicated. Any questions? Any more administrative questions? All right, so let's talk about science, experiment, and theory. This is an overview of the scientific method. And it goes circular, it goes round and round. How do you use the scientific method in your everyday life? Yes. Yeah, you can go. Thank you, TAs. All right. All right. They will be very helpful. Okay. So, how do you use the scientific method in your everyday life? Huh? No, so I hear some gurgling. I hear some things. How do you use the scientific method in your everyday life? Sure, Federico, what do you think?
You see a problem, and then how do I solve that problem? So, think of an example. Let's say you have a bad sleep schedule. You observe that you have a bad sleep schedule.
Right, bad sleep schedule. Okay.
You want to fix your sleep schedule. So one way is to make a schedule during your daytime so you go to sleep at a reasonable time. Another time is to do some exercise if you're tired at the right time. That's maybe one way. Just kind of a weird idea.
Yeah, okay, so you're trying to optimize your energy levels by at least getting some sleep. Yeah? How did you choose whether or not to have breakfast this morning? And what did you choose for breakfast? You observed you were hungry. And you've probably done some experimentation in the past about what you like for breakfast, what will get you through the day. Or maybe you don't need breakfast this morning because you got the rush to class or something, right? Right, and so this cycle goes round and round and round, okay? We're going to focus on the hypothesis quite a bit. Nonetheless, you've got to do some observation. You've got to look into the topic a little bit before we can formulate this hypothesis. And if you're getting stomach cramps, in the afternoon, and it's because you had donuts for breakfast 5 days in a row, right? You could continue to test that hypothesis, or you could go and say, hey, I've already done enough of this, I got enough analysis, I can conclude and write my report. If I eat donuts 5 days in a row for breakfast, my stomach's not going to feel so good. Okay. Or maybe you have an iron stomach and it doesn't matter. Okay. But we use the scientific method all the time, every day. Okay. And we can form testable hypotheses. We can experiment upon them. Okay? We can draw some conclusions. And we can make a report. Okay? So, empirical studies. Now, what does an empirical study really mean? What is something that's empirical? Yes?
It's like it's evidence that just gather from basic analysis of like environment.
Yes. Okay, that's good, right? You don't necessarily have a model, right? It's not like I've got the PDEs all lined up to describe my stomach and what happens to it, right? And they're running. Like, I just don't have that, right? And in empirical studies, I mean, it can be done on models as well. Okay, we'll show an example in a minute, okay, of how that works. But again, you're kind of doing an experiment. You're an experimentalist. You don't get too. Sometimes you get bogged down, but you're gonna kind of say, hey, how can I learn something, right? And so you put the hypothesis after some observations. You do some design of experiments. You execute the experiment. You collect the data. You might even do repetitions to get some statistics, some means, some standard deviations, some whatever, standard errors, whatever it might be. And then you analyze the data and you make some conclusions. And then you can go ahead, after you've done that, and you need another grant, create another hypothesis. Okay? And try to test that hypothesis and see if the people with the money will let you do it, right? This is something that's been going on for years and years and years, right? Happens in business, happens in science, happens in engineering. Okay? So when you go through this process, there are some pros, all right? One is the experiment always wins, okay? Now, what does that mean? That's something that we talk about in our lab, because what are we? We're generally experimentalists, okay? So experimentalists will tell themselves that we win all the time. But you can have bad experiments that then cost you money, time, and career, right? Which those are not great. A well-formed experiment, though, will lead to new knowledge, and it will generally give material for the people who focus more on the theory, for the simulation, to use as they go along and develop more theories. It's really great when theory informs experiments. Okay, so physicists do that a lot. And whatever, Higgs boson and various different things, you know, a lot of stuff that Einstein thought was possible, the experimentalists came after. In many cases, though, in engineering, it doesn't make sense to model the car before you've made it. Okay, so if you've got an automobile, you're not gonna create the simulation for every single component and show that it can drive before you do that, right? You're going to take some reasonable understanding of engineering, get the different components together, and put it together. And then simulation, usually for automotive engineering, will come into play with the optimization, right? Trying to make it better. Empirical studies, though, because they use real materials, and materials can be expensive. They use real processes, machining, forming, designing, measuring, all that stuff. It can be expensive. Okay? Could even be impossible. All right. So there's some clever things you can do. Astronomers have been doing clever things though for for a long time, right? They've got the whole galaxy as their, or the whole universe as their playground, right? So they can make observations, but you know, trying to figure out exactly what's on some planets and some planets regolith it might just not be possible for now. Okay, can also be very difficult to figure out what is affecting what. So in optimization, one approach is to use what's called one factor at a time optimization. So you just change one factor and you look at the results, but you could still have compounding effects. Okay. So Johannes Kepler, we're going to do particle dynamics. We're going to do some orbital mechanics very soon. Okay, it'll be fun. And Kepler, he is an astronomer, and he published these tables that he had some funding. He also had some funding that allowed this to happen, that were kind of based on observations. Okay, so he was able to kind of figure out, oh, these things are orbiting about each other, and this is how long it takes, and I can set up a set of experiments that record these times. Okay, and this empiricism was awesome because it got people observing things. People saying, hey, we have an Earth, orbiting around the sun, and this is how it's doing it. This is how fast it's doing it. Okay? So he came up with some laws. Right? And so here's kind of a summary of them. An orbit of a planet is an ellipse with the sun at one of the two foci. A line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. And the square of a planet's orbit period is proportional to the cube of the length of the semi-major axis of its orbit. Okay, so he was able to kind of make these relationships or come up with these observations. Is this a model? Well, kind of. I mean, it comes up with some rules. These are observations. This is empiricism. But who really got the model right? Sir Isaac Newton. Okay, so Newton said, "Hey, we can describe the interaction between masses in terms of gravity, and I've got a little bit of math. I've invented calculus, and so here are the relationships, and I can now make predictions." Okay? So Newton's laws of motions come around. Newton's laws of motion come around, and we have these three. Okay? And in this case, yes, it's just words, just like Kepler's were just words, but there's a bunch of math that goes behind it, as you know, and he was able to come up with this idea of universal gravitation, the big G, all right, between masses, and he can now calculate orbital periods just like Kepler was observing, and we have an analytical solution. So this is an example of empiricism leading to essentially a model and an analytical solution that's usable. Right? Now, you could argue that, not to say that, Newton was also an empiricist, right? He was observing the world around him as he was making his discoveries. And so it's not to say, oh, this theoretician didn't use any empiricism. Of course there was empiricism and observations and logic surrounding. He did not spend as much time, though, calculating these observations. So we get to a point where we get analytical solutions. And there are pros and cons of analytical solutions. Pros are an analytical solution is often simple to calculate, often inexpensive, simple to validate, and it's going to be accurate, okay, within some bounds. Cons are it could be inaccurate, and sometimes they do not handle the complexity of the real world, and the laws of gravity, for example, do not handle relativity, right? But as long as you're not going too close to the speed of light, although satellites, right, and the timing that that's required there, again, within some bounds, you're going to be, you're going to be able to describe most of the things that we're considering. And there's also this thing that there's not an analytical solution for 3-body orbits. All right, so you have 2-body orbits, fine, you can describe that, but the interactions between, say, 3 bodies that are trying to orbit around each other, there's not a simple analytical solution to that. So, what is an alternative to closed form solutions or analytical solutions? Well, we're sitting in it, right? This class, we could simulate it, right? That's the alternative. We can make some approximate models, and we can simulate, right? So here, essentially what you can say is you can break a problem down into these, so Newton has his laws of gravitation, right? Maybe there are some ways, like we'll talk about when we do particle dynamics, maybe there's some ways that we can use those mathematical laws not to come up with an analytical result, but to come up with a simulated result. Okay. This is my slide from mechanics and materials. There's a synergy here. Yeah, okay, you're like trying to shut it out, right? There's a synergy between the closed form solutions, the analytical solutions, and the simulations. That synergy, right, is what I like to call the baby step. First, get your simulation to work on something that you know, or you have a reasonable belief that is correct. After you've got that, make it more complex. Okay? Now, how do you write a paper in the last few minutes? I suggest reading this paper by one of my advisors, former advisors, okay? And it's about writing a paper. And it talks about what a scientific paper is. So the introduction often includes your reasoning for doing what you're doing and what the hypotheses are. Then we go into results and discussion and conclusions. So these are kind of the basic sections. We'll have slight, we can sometimes just can split results and discussions, all right, data discussions. Often we do. And so this is kind of the working format for your paper. Here are some ideas of what goes into the introduction. Okay? First paragraph or two should be written out completely. Right? Talk about the objectives. Talk about the justification, the background. Give us some guidance. Essentially, it's the exposition of your story. Right? What are the elements of a story? Go ahead. The basic elements of a story. Hold on, someone else. Huh? The setting, all right? The exposition, the setting, then what comes next? The rising action, the development. Then what comes next? The climax, all right? And then what comes after that? Right, the denouement, right? Okay, perfect. That's what we want with your reports, okay? And so to conclude, I look forward to seeing you all here. Half of you for time. I hope you'll enjoy this class. Thank you for sticking around for this introduction. And see some of you on Thursday.
I am not added to